Okay, thank you. This is joint work with Véronique Courtier, François Duplessor, Benedict Smith, Pierre-Yves Straub, and Bogdan Varinsky. So electronic voting is an important part of our democracy, and its current electronic form has been used in an ever-growing number of elections and referendums. All countries have some kind of similar or common steps, but each of them, depending on their legal or socio-political context, may lead to different solutions. For example, in France, and I'll let you pick it up on the map, recently it offered both machine voting or also internet voting, but this year in March, they stopped providing internet voting for overseas voters among fears of cyber attacks. So, besides those countries that already have using some kind of electronic voting form, there are other countries that are trying to do discussion or plans. So a natural good question will be, what kind of properties should this protocol satisfy? And one of those is privacy, and essentially says that votes should not be leaked. Then you may have additional properties such as verifiability, that will allow voters to check if their vote was counted and receive freeness on coercion resistance that offers some kind of protection against coercions and so on. One protocol, for example, that also provides privacy and verifiability is Helios. Then you may have Helios, which is a variant of Helios, but in addition to these two properties offers in its latest form receipt freeness. Then you may have Civitas, which offers besides privacy and verifiability coercion resistance, and I could go on and on. The point that I'm trying to make is there are a lot of voting protocols, each with their own definition and a security proof depending on which property they satisfy. In addition to that, there are a lot of while there's a consensus on what the intuition of properties are, their definitions is still ongoing research. And most of the proofs are done by hand, so they are error-prone and difficult to check. There's also, in recent years, a desire to shift from just analyzing algorithm description to more of implementation level of details. And this is where formal methods come to help us, and EasyCrypt is one of those tools. Essentially, it's an interactive proof assistant for the computational model. It has been proposed in 2011 to deal with cryptographic primitives. Since then, has been applied successfully in pairing-based cryptography, multi-party computation, and side-channel security. And would like to also apply the same security guarantees that EasyCrypt provided for those applications to electronic voting. More specifically, we used a general framework to ensure machine check for privacy. Then we instantiated our result to hundreds of variants of Helios without having to redo all the proofs for each of them. The basis of our work is on a key construction called mini-voting. It has been introduced in 2011. It just presents a natural view of a voting process. So you have a voter that constructs a ballot by calling the include vote algorithm. It's submitted to a voting server. The server may do some validation or not on the ballot before adding it to the ballot box. And this process will go on and on till the voting phase ends. And then you, at the end of the voting phase, you have the computation of the result and a proof that this one was done correctly. There's also the possibility of the voter to check if this result corresponds to some public information. Another important privacy, it's intuitively easy to define. It says that others should not be able to infer how you voted. But the definition is kind of difficult, as there are different models of how to deal with it. There are also symbolic models and computational ones, so we'd like to select the computational model to better fit our tool. And then there are two main definitions, simulation-based and game-based. They're both widely accepted. We just select one of those, and it is a definition that was introduced here 2 years ago by Bernard, Galindo, Courtier, and Varinsky. And the key feature of that definition is ballot privacy, and essentially it says that ballots should not reveal information about the votes. And the main contribution of our work is based on this simple theorem, but it took much effort just to prove it in a script. And we were able to do that with two basic assumptions. One on the construction of the ballots, and the other one is on the proof for correctness of the result. So now, given this highly abstract result, meaning voting is ballot private, we'd like to, bring it closer to real-world application. So let's play a little bit with what we can do. So for example, we can offer different ways of computing the results. So we can consider mixed nets or homomorphic addition. So for homomorphic addition, you have a list of ciphertext. They are compressed so that you obtain a single ciphertext. By decrypting it, you obtain the sum of all the votes that were in the initial ciphertext. And for mixed nets, you have a sequence of mixed servers that they reshuffle stuff, and then they do the final decryption. In addition to that, you may also like to decide which vote to keep. In real binding election, they don't allow revoting. So you're forced to vote only once. But in internet and academic protocols, you can revote multiple times with just keeping the last vote policy, for example, or you can do something like just keep everything. In addition to that, you can also play a little bit with what you offer to the voters. So in France, for example, it's mandatory not to publish anything. So of course, you also have the first option. While in Helios, for example, you can publish all the information of the ballots, so nothing is hidden. But also in Helios, you can publish only the last ballot that is used to compute the result, or you can simplify what the voters will see, so applying a hash of the entire ballot, or you just can provide a simple anonymity, just removing the identity of the voters and just providing a list of ciphertext. You may also like to decide if your scheme will be verifiable or not. This has a direct correlation to what is available. For example, if you publish nothing, it's impossible to obtain verifiability because you'll have just the result of the election and nothing else. So otherwise, you can play with all the variants as you want. It will also be possible to do some validation tests before adding it to the ballot box. So it's not necessary, but you like to be sure that the ballot box contains only valid ballots before sending it to the tally algorithm. So now let's go through some real implementations. One of those is Helios version 3 with mixed nets. And we're able to do that by simple instantiating all the variants that we discussed previously. So for tally, we consider mixed nets. We also keep the last vote policy. We say that the scheme will be verifiable. Then also we publish the last ballot, and we decide that to introduce only valid ballots to the ballot box. So now, how would we prove that this construction satisfies ballot privacy? So we already have this result that's saying ballot privacy is mini voting is ballot private. So in case you need to pay careful attention because this one is really difficult, so you may miss it. So this one is done because of the magic of EasyCrypt. So it's a modular system that allows proving it. So allows proving abstract stuff for general context, and then instantiating this to particular context, such that when we get to the latest version, we just need to show that our instantiation satisfies some abstract assumptions, and then we also get ballot privacy for free. Another option in a real implementation is Helios version 3 with homomorphic addition. The difference between these two is related to how the result is computed. So you have the first option where you have homomorphic addition, and then you can play with many other variants. So this one will be a good point you to our paper, where you have a link to a tool where you can create all these variants or a specific one, and you can also ensure it satisfies privacy. Okay. Now, as I mentioned, ballot privacy is our main contribution and our main result, but also in the initial paper, it has been shown that ballot privacy is not enough to satisfy privacy. One example will be, so the intuition is that ballot privacy looks at how the ballot is composed. But what if the case of the tally algorithm gives you a list of names and results? This is still ballot private, but it's not something that we want to say is private. So one solution will be predefining what the result will be and enforcing the tally algorithm to do that. That is called strong correctness. Another example will be the possibility of rejecting ballots before adding them to the ballot box. This will be also ballot private, but it's not something we want. So this is enforced by another property called strong correctness, where voters can create ballots freely by calling the correct algorithm, and then we will successfully add them to the ballot box. In addition to ballot privacy, we also show that mini-voting satisfies these two additional properties. They've been proven as a script. These ones are really important, especially because one of those properties, strong correctness, is an essential part of trying to show ballot privacy for mini-voting. The intuition for that is that ballot privacy looks at the ballots, but what happens when you reject a lot of ballots before adding it to the ballot box? So strong correctness tries to enforce that for honest voters, their ballots will be successfully added. Another interesting aspect that we had to deal was random oracles. Most of the times it is usually skipped on pen and paper proofs. And in our model, we had to deal with it at the beginning of our result. I mean, luckily it was true, but it was more complicated because we had to insist that our voting scheme has access to a random oracle, then saying at the end of our proof it is possible to put a voting scheme with random oracles in what we have. Okay, now trying to present some kind of statistic on the number of line of codes and verification time. I think on your right, you have voting stages and the most important ones, and on the left you have number of lines of codes and verification time. So as you can see, most of our work has been concentrated on mini-voting. Then you also have a lot of examples, 540 to be exact, and all of them had been proved to be private using EasyCrypt. So for example, if in case you don't trust us at all, and you just want to show one of those variants, you have to do the verification of all the components. But if you just trust us, you'll only need 3.4 seconds to verify a single variant. Okay, to conclude, we proposed a machine check proof for privacy of a voting protocol. It is the first machine check proof of privacy in the computational model. It is sufficiently general to capture hundreds of variants of Helios. And as ongoing work, we already started and almost finishing verifiability, and would like to continue expressing our work to other voting systems like Select, Cătalin, Helios, and maybe Civitas, but also other properties like accountability. Okay, thank you.
Merci. This is very nice work, as far as it goes.
Yeah.
One thing you have apparently completely ignored in the talk, but it may be in the paper, and I haven't read it yet, is the question of system integrity. If you can't trust the operating system, you can't trust the hardware underneath, and you have insiders who are determined to rig your election, have you thought at all about what it would take not only to extend your proofs, which are very nice, but to understand fully the risks of an election being compromised using this particular system?
I mean, so the issues related to our definition of privacy, and those in the model of privacy that we consider is that the ballots are created honestly by voters, so there's no malicious interference. But we'd like to explore some real-world application where the model is more detailed on what can happen. But unfortunately, in the current stages of our work, we don't consider that. But we'll plan to do that. I mean, probably after verifiability, we'll like to consider some real-world application.
Other questions? Okay, so you verified like hundreds of variants of the voting protocol. Were there any that failed to verify that you looked at?
So the issue is that no, we didn't. So we tried to just generate variants that we already know they are they are private, because it's based on our assumption. So our cryptographic assumptions were minimal. So if those variants don't satisfy our cryptographic assumptions, there was no point of generating them and having some kind of proof. So all those variants that were generated just use the proof from BNI voting and show that those variants satisfy ballot privacy.
Okay, so you kind of like looked in the right places and then just verified that your assumptions were correct that way.
Yeah. So I mean, we started with minimum assumptions. So if they satisfy these two basic assumptions for the encryption and zero knowledge proof system, then all the voting schemes that can be instantiated should be okay.
Okay. So we have a few minutes. We're a little ahead of schedule. So
yeah, sorry about that.
Oh no.
I think I'm the first one that talked faster.
All right, but if there really aren't any other questions, let's thank our speaker again.
Okay.